In the last lesson, you learned that different materials can be used in the negative electrodes in lithium-ion battery cells. If you remember, we looked at graphite and at lithium titanate and also at silicon. In this lesson, we are going to look at materials that can be used for positive electrodes instead, and it turns out that there are many more options from which we can choose. The first intercalation material that was discovered for positive electrodes in lithium-ion battery cells was lithium cobalt oxide. And this material was discovered in 1980 by Professor Goodenough and his research team. The atomic crystalline structure of lithium cobalt oxide is drawn on this slide. Cobalt is shown as dark blue spheres, and oxygen is shown as red spheres. In the structure on this slide, cobalt and oxygen form very tight electrochemical bonds with each other, and these are not affected by lithium moving into and out of the material. And so because these bonds are constant, they're shown with these planes, the blue planes that show the surfaces formed by the crystalline structure of these bonds. When lithium enters into the electrode and when lithium leaves the electrode, the structure of the lithium cobalt oxide is not actually changed. It does not disturb these carbon oxygen, these cobalt oxygen bonds. As you see in the figure, the overall structure has layers of this cobalt oxide material, a lot like graphite has layers of graphene. And because cobalt oxide has this layered structure, it's often called a layered cathode material. The lithium atoms are free to enter and exit and to move around the space between the cobalt oxide layers. You'll notice in the chemical formula in the third bullet point on this slide that the subscript for lithium is X. This might not seem common to you. It might seem unusual if you're more familiar with chemical formula like H2O, where the subscripts are all integer numbers. The X in this formula is there to show that there is a variable amount of lithium in this structure. If there's no lithium at all in the structure, then X is 0. If the structure has as much lithium as it can possibly hold, then X is equal to 1. And if the structure has some amount of lithiation but not full lithiation, then X is going to be a number between 0 and 1. And so we see that X is not describing what's happening right at one point in an atomistic scale. It's actually an average over the whole electrode, or at least over a local region, of how much lithium is present, which is why it can be a fractional number. So as we charge a battery cell and discharge a battery cell, this value for X is going to change. The value indicates an electrode state of charge, and it's what we called a stoichiometry in the last lesson. Lithium cobalt oxide actually makes quite a good positive electrode material, and it's in very common use. You find it in a lot of portable electronics and laptops and mobile phones. But there are some challenges when we try to scale up the lithium cobalt oxide for very large battery cells for very large applications. For example, thinking about vehicle use or utility grid use. One of the problems is that cobalt is very rare, and so it's expensive. It's also a toxic element, and so we don't want to have too much of that getting thrown out by accident and entering in landfills. Another challenge with lithium cobalt oxide that may not be readily apparent is that we can only use about half of its theoretic capacity. If we think about the value of X in the subscript for lithium on the previous slide, the value of X can really only go between about 0.5 and 1. If it goes below 0.5, we have some capacity degradation issues that happen. So in order to make this material more practical for large-scale application, researchers have substituted different elements for some of the cobalt in the structure. If we substitute all of the cobalt with nickel, we end up with lithium nickel oxide, and that actually has a higher energy density for the same amount of material, so we can store more energy. Lithium nickel oxide, however, it has the higher energy density because it has higher voltage, which is nice, but it also suffers from being less stable thermally, meaning that if you overcharge the battery cell, it's more likely to combust, and that's, of course, very undesirable. It's also possible to substitute other metals. For cobalt, we can substitute aluminum or chromium or manganese, and these all give slightly different properties when we do so. Maybe the most popular substitution presently is to replace some of the cobalt with nickel and some with manganese, and so we end up with a nickel cobalt manganese or NCM material. And this material has exactly the same atomic crystalline structure as you see on this slide. It's just that some of the cobalt is replaced with other elements. The nickel in the structure tends to increase the voltage, and the manganese tends to make the material more thermally stable, which is a desirable property. At this point in history, many automotive battery packs are made with this NCM or NMC type of battery cell. Another alternative is to replace some of the cobalt with nickel and some with aluminum, and this is an NCA battery cell. And this is the type of battery cell that's used in Tesla automobiles at this point in time. We can investigate a completely different structure for positive electrodes, which is lithium manganese oxide, and this material was also discovered by Professor Goodenough and his research team. The image on the right of the slide shows the atomic scale crystalline structure of this material, and the blue spheres are manganese in this case, and the red spheres are oxygen. This structure might look familiar to you if you have a good memory. It's what we saw in the previous lesson for lithium titanate oxide, which is a possible negative electrode material. The name of this crystal structure is cubic spinel. And as you can see, there's many internal vacancies that could hold lithium, but these vacancies are organized, if you will, in convoluted, twisted, three-dimensional pathways that allows the diffusion of lithium in three directions. And it's difficult to see this in a static picture on a slide, but it happens that lithium can enter in from both sides, it can enter in from top and bottom, and it can enter in from front and back as well. So from all three directions. And because of that, we call this a three-dimensional structure. If you contrast it with the layered structure of lithium cobalt oxide, in that structure lithium could enter front and back and left and right, but it could not enter top and bottom. So lithium could move only in two directions, and we called that a two-dimensional structure. And on the next slide, we're going to see a candidate positive electrode material where lithium can enter only through one direction in tunnels, and we call that a one-dimensional structure because of that. In the chemical equation for lithium manganese oxide, notice again there's an X in the subscript for lithium, and in this material X can go from 0 all the way up to 2, which is different from what we saw in lithium cobalt oxide. However, if X is larger than 1, the material tends to dissolve in the electrolytes commonly used in lithium-ion battery cells, and for that reason we use X from 0 to 1 almost always in practice. A huge advantage of the lithium manganese oxide versus lithium cobalt oxide, or even NMC or NCA, is that it is less expensive because manganese is very common, and it's also safer. But the drawback, as I've kind of hinted at already, is that it can have short life. It turns out that the manganese in the structure is very susceptible to acidic electrolyte conditions. Now, we don't make acidic electrolytes on purpose, but if there's any moisture in the air when we are building this cell, this moisture gets absorbed in the electrolyte, and it can combine with some common electrolyte salts, and the hydrogen from the water and the moisture and some fluorine from the salts can combine into hydrofluoric acid, HF. This hydrofluoric acid is really terrible stuff, and it's a very powerful acid, and it can eat away at the manganese and the lithium manganese oxide. And so the manganese can dissolve, and so the positive electrode structure basically dissolves, and there are less vacancies that are able to hold lithium, and so we have capacity loss. So when we build the cell, we try to eliminate moisture, but it's not possible to eliminate it completely. We build the cell in an environment where the electrolyte is injected in what's called a dry room, where we've evacuated as much moisture as we reasonably can, but there will always be some moisture in the electrolyte. So much of the research that you see in the literature, you're going to find people talking about lithium manganese oxide battery cells, and a lot of that is because it's quite inexpensive to obtain the material for a research lab, and it's quite inexpensive and easy to obtain. And because of that, because a lot of research is done with the material, you will also see a lot of papers where people investigate ways to prolong life. Sometimes they do that by adding different chemicals to the electrolyte that preferentially scavenges the acid, so that the acid attacks these added materials instead of attacking the electrode itself. And sometimes you see people coating the electrode particles with something that protects the particles from the acid. Any battery cell that uses lithium manganese oxide is going to have something as part of its design in order to extend its life, but it's usually not disclosed to you exactly what that is. It's a trade secret almost always. A third variety of positive electrode active material was once again discovered by Professor Goodenough's research team, and these are the olivine style phosphates. The most commonly found member of this family is called lithium iron phosphate. This material is very inexpensive, and it's very non-toxic, and that's all fantastic. But unfortunately, it also has low energy density because of the low open circuit potential of the material, as we'll see later on. And it also has low specific energy because iron is a very heavy element. Its structure also makes it difficult to get a lot of power out of the material, so it's often a low specific power material. The image on the right of the slide shows the structure, and in this image, iron is represented by the brown spheres, and phosphorus by gray spheres, and oxygen by red spheres, and the lithium, again, as purple spheres. And in this overall structure, the iron oxide, the FeO6, forms the brown octahedral crystal shapes, and the phosphate, the PO4, forms the gray tetrahedral shapes. And in the image, you can see that the lithium atoms can go only one direction into these tunnel-like vacancies in the structure. It's not free to flow in 2 dimensions like it is in a layered cathode, or in 3 dimensions like it is in a cubic Spinel cathode. And so that tends to reduce the power that's available. The most common way to solve this problem is to use extremely small particles in our positive electrode, which means that the diffusion distance is very short, and therefore the diffusion overall can happen more quickly, and we can get a lot of power out. But we require very small particles to do this. Another challenge using the material is that it has very low electronic conductivity. It's difficult for the electrons to move around in the active material. And the way to get around this problem is by coating the material with conductive additives like carbon black, so that the electrons can flow on the surface of the particle through the carbon black from the electrode to the current collector and out of this cell. There are different candidates for positive electrode materials, but I've shown you the most common ones. Most of what you see that's different from this are simply mixtures of these where some optimization has taken place to attempt to get the most desirable properties from 2 or 3 different materials at the same time by combining them in what we call a blend electrode. So in summary, in this lesson, you've learned about the materials that are most commonly used in positive electrodes in commercial lithium-ion battery cells at this point in time. Since essentially every lithium-ion battery cell on the market has a graphite negative electrode, the distinguishing factor between the chemistries of different cells is therefore what is going on in the positive electrode. And so it's quite common to refer to a cell by the chemistry of its positive electrode only. We might talk about a lithium cobalt oxide cell, or we might talk about an NMC cell, or a LMO cell, or a lithium iron phosphate cell, or something like that. And you've already seen that you can predict a little bit about the different power capabilities of this material depending on whether it's a one-dimensional or a two-dimensional or a three-dimensional structure. It also turns out that these different materials have different voltage properties that lead to different energy densities. Remember that the voltage of a battery cell is equal to the potential at the positive electrode current collector minus the potential at the negative electrode current collector. Therefore, for a high voltage battery cell, we would like to have a positive electrode that has a high potential. The figure on the right of this slide shows the open circuit potential of these different electrode materials as a function of how much lithium is in them, their stoichiometry, or the electrode state of charge. You can see that lithium iron phosphate has the lowest potential of all of those that we've considered. This means that lithium iron phosphate cells tend to have low energy density because of this. You can see that other types of positive electrode materials have slightly different voltage characteristics, but all of them turn out to be higher than lithium iron phosphate. When we come to the third course in the specialization that talks about estimating state of charge of a battery cell, we're going to find that the different voltage characteristics of these materials is also important at that point. You're going to learn that the accuracy of a state of charge estimate depends quite heavily on the information that is conveyed in the voltage signal that we measure. And simply by looking at the graph on this slide, you can already begin to predict some qualities of estimating state of charge using different materials. In particular, notice that the iron phosphate curve has essentially no change in voltage over about 80% of its state of charge range. This means that the voltage I measure at 20% electrode state of charge and the voltage I measure at 80% state of charge are almost exactly the same. And so by voltage only, it's going to be very difficult to distinguish what state of charge is for battery cells using this material. Looking at the other materials, we see that lithium manganese oxide also has some flat spots in its overall profile, but it is a little bit less flat overall than iron phosphate, and so it's a little easier to estimate state of charge for an LMO cell. And looking at the NCA and NMC cells, you might imagine that it would be easier to estimate state of charge well because there's a fairly consistent slope or a fairly consistent change in voltage across the state of charge range, and that actually is true, that these tend to be the easiest cells to write good state of charge estimation algorithms for. So when you choose a cell chemistry in the design of the battery pack, there's going to be implications beyond simply energy density or power density. There will also be implications on the ability of the battery management system to regulate the activity of the battery pack. So to wrap up, remember that layered positive electrodes can use only about half of their theoretic capacity. I didn't explain why, but it turns out that if you take too much lithium out of those layers that separate the cobalt oxide layers, the layers will tend to collapse and it will not be possible to insert lithium between the layers anymore. So we need to keep about 50% electrode state of charge or higher to make sure that the layers don't collapse on each other. We learned that the olivine positive electrode materials have low voltage and give very little state information in that voltage as well. and that the Spinel positive electrodes are inexpensive and non-toxic, which is great, but that they also tend to degrade rapidly. So there are advantages and disadvantages of all of these materials. It doesn't matter which one you choose. It turns out to be an engineering effort, as always, to balance the trade-offs to find the best one for your particular application. So that brings us to the end of this particular topic, and from here we're going to move on and look at the electrolyte, the solvent and the salts chosen for lithium-ion battery cells, and also the separator.